new insight into medical protocols 1A from empirical sea level reconstruction and numerical modeling. And the supervisor has been Christian Vaskog and co-supervisors Constance Havner and Jon Inge Svendsen. And in the committee assessing this is Anna Solmundset from NGU and myself, Kanya Solgren from the department. So the floor is yours.
Thank you. Thanks for introducing my master's title. I'm going to talk to you about novel plus 1A from two different approaches, which makes this study quite unique. So I'll try to take you through it within these 20 minutes. So I will first introduce the topic of the project, then discuss a little bit about where we are in the world, and then I will go through methods and main findings from two different perspectives, and then the synthesis chapter 5 aims to bring these together, and then I will draw some conclusions upon them. So, the introduction. Why study past sea level change? So understanding past sea level dynamics is crucial for future predictions of sea level change, and currently under global warming, ice sheets are melting at an accelerating rate, causing a global rise in sea level. However, these future projections of global sea level come with quite a large uncertainty, which you can see over here. And this means that we need to know more about how fast will the large ice sheets melt and how will sea level respond to that as a consequence. In addition to that, sea level change is not spatially uniform around the entire globe, and this is because of something called glacial assisted adjustment. So to just quickly explain what that means, this figure, you can see here an ice sheet that is first stable, then loses ice mass, and this ice mass reduction, this reduced load of ice mass on the solid Earth, needs to respond with the solid Earth because it starts to lift up, and that is what we call glacial ice adjustment. This causes a lowering of sea level in the near field, but the melt from the ice sheet is causing a sea level rise in the far field. So it's very different spatially. And in addition to that, there's also reduced gravitational attraction in the near field between the ice sheet and the ocean, leading to even more pronounced lowering in close proximity to the ice sheet. So we can learn from the past, because this is not the first time that ice sheets are starting to disappear. It happened before, right where we are today, because there used to be an ice sheet covering the entirety of Scandinavia, the Barents Sea, and also the northern part of the UK and Ireland. This is called the Eurasian ice sheet. It started to retreat around approximately 90,000 years ago, and then a period that is very interesting to study is now what it calls 1A period. This occurred between 1465 to 14,000 years ago, and it was a global event during which a warming in the northern hemisphere led to a simultaneous melt of several ice sheets, and this led to a global sea level rise that is 10 times the rate of what we are experiencing today. So this was a huge event of a very rapid ice sheet collapse, and we can learn from that by studying it. However, the deglaciation history of the Eurasian ice sheet is quite highly uncertain during the melt-over-falls warming period, and this is because of problems that we have with the radiocarbon dating method in this time period. And specifically, it has to do with the marine reservoir effect, which is fairly unknown during this period. And that is where both modeling and empirical data comes in, because we want to test different ice thickness scenarios of the Eurasian ice sheet in this time frame to see how sea level would respond to that, and also to see how much the Eurasian ice sheet might have contributed to the sea level rise during the melt-over-falls warming. In addition to that, we want to use empirical data from the near field. So we're located very near field, This is the maximum extent of the Eurasian ice sheet, and we are located on the southwestern coast of Norway. And empirical data in this area from the near field can help to validate models, which can then also be used in the future to make future sea level change. So my main research question is how did relative sea level change through time during the late glacial of Buchan, an island located on the southwestern coast of Norway, specifically in relation to meltwater plus warming. Then I have some sub-questions and other aims. I want to know how high the highest sea level after last deglaciation is in marine limits. And I want to investigate the contribution, or like potential contributions of the Eurasian ice sheet during meltwater plus warming. This is a very highly debated topic, and it is elusive so far, so we want to investigate this, and then I want to zoom in on Buchan after that and look at the impact of different ice thickness scenarios of the Eurasian ice sheet and see how that reflects locally at the on sea level at Buchan. Then the sea level model that I'm using, I also want to do a sensitivity analysis to see how it responds to changes in different components, how sensitive is it to these components. And then the last one is about the chronology of the glaciation of the Eurasian ice sheet. We want to test what happens if we use a different calibration age for this ice history. And then we're using an increased free willing marine reservoir age proposed in a recent study, the whole study. So, the study area. Located on the southwestern coast of Norway, it's an island, and it has previously been very well studied for relative sea level reconstruction purposes. You can see on this map some isolation basins that are marked in gray. These have been used previously to construct a relative sea level curve. And then I am studying two different basins marked in red to improve this pre-existing relative sea level curve. So first of all, an isolation basin named Sør-Jærenvatnet, which is located very close to the coast of Buchan. And then the second one is Buchan in a depot, which is located at a higher altitude than Sør-Jærenvatnet. So the methods. For the empirical reconstructions, I use the isolation basin approach. An isolation basin is the basin that once used to be below sea level, but at some point in time has been isolated from the sea due to changes in both the bedrock but also sea level. And these changes are reflected in the depositional environment of the lake. So when one takes a tour from this lake, you can see these changes in environment in the sediments. And yeah, that is what I will shortly take you through. But first, we had to go to Sør-Jærenvatnet last year in June to collect the sediment core. You can see us doing that here. It was very nice weather, and we used a piston core to collect the core. Yeah, that all went very well. Then we went to the bog. Still very nice weather. A little bit more insects, so maybe a little less comfortable. But yeah, so here we use the Russian peat for collecting core. That's very good. Then I went into the lab in the autumn, and I used several sedimentological proxies, but also a biological proxy to distinguish between the shifts in depositional environment in the core of Sør-Jærenvatnet. And then I also wanted to date the core by using different dating methods, secret gene dating, radiocarbon dating, and vector analysis. Maybe nice to know the pipette length, very indicative of marine or lacustream conditions in the lake because they have a different salinity tolerance. So they were used for that purpose. Then I used a sea level model. It's a global model, and it adjusts bedrock and the chemistry of the globe according to changes in ice load. So it's basically doing what I explained on one of the first slides. It's accounting for the gravitational attraction, the isostatic adjustment, and the changes in ocean volume. I started my simulations in 26,000 years ago, and I ran them until 10,000 years ago. And the focus was, of course, on the period where we had the meltwater plus 1A, but also until 10,000 years ago. Yes, the model has different inputs. I will go more into detail on the next slide. This is just a short overview. What I want to point out here is that the Earth model consists of 3 parameters, and you need to supply the model with the Earth model in order for it to do these GIA calculations. Yes, so, and then as an output, you can get the local relative sea level changes over time. But for the ice flow history that I supplied the model with, I used I6G for ice sheets around the globe. And for the Eurasian ice sheet, I used a very recent ice thickness reconstruction from, say, 2022. And I merged these to get the best possible ice thickness history for this site. Then I used 3 different Earth models, which are listed here. The VM5A model is commonly used in combination with I6G ice thickness data. And I used 2 different time series. So first, the original one that came with this ice thickness history, and then a revised series where I recalibrated these dates using this new marine reservoir age proposed in Blending in 2020. Then I want to quickly point out that the most normal settings, or what I consider normal, are called the base run, as I said. And the reason that I'm testing all of these different inputs is because I want to know the sensitivity of the model to these different parameters. So in order to be able to compare it to something, I need a base run. And the base run has the most normal settings here. So the original time series, the impact Earth model, and the merged ice thickness data. Then I set up different experiments. I'm not going to go into detail for experiment concept 3, simply because I don't have the time, but if you have questions, I would love to answer them after. Experiment set 1 was testing different ice thickness scenarios for Eurasian ice sheets, and number 2 was done to isolate the signal from the Eurasian ice sheet to the rise in global sea level that we see during meltwater plus 1A. And I did this by keeping all the other ice sheets around the globe stable, and only adjusting to only the ice mass of the Eurasian ice sheet was shrinking over time. Oh, very complicated, but I will move on to my main findings. So for the marine limit at Buchan, we went to this bog that I showed you the nice video of. And this bog is located slightly higher than the minimum constraint of the marine limit so far, which is at 20.95 meters above sea level, which was constrained in the study by Stone since 2019. So I was curious, we know that sea level reached up to this altitude, just slightly, but does it then reach to the higher altitude? So we went to a bog that has an outlet threshold of 22.5 meters above present day sea level, and we saw that there was no marine input in that basin. So we could constrain maximum constraint of marine limits, and then the average becomes 21.73 at present. So this was very nice. And then we also saw that the timing of the marine limits was most likely shortly after the deglaciation of Buchan, which was around 15,060 years ago, according to Stumsness, which is an age that we agree in this study. Then moving on to a lower altitude, so you can see here, so there's a volcano slope a bit lower, which means it has been below sea level in the past. And this slope, or this isolation basin, was used to reconstruct sea level index points for the to improve the pre-existing curve. So it's a very complicated figure. I'll try to take you through briefly. So this is a picture of the core. Then we have the litmus stratigraphy next to it. We have can I hide this? No. Yeah, great. And then we have the phytoplankton over here. the loss of emission, which reflects organic content, and we have magnetic susceptibility to geographic uses. So in general, changes in these can reflect a change in depositional environments. And what's very striking in this figure is this spike over here and here. And this yeah. This corresponds to a tephra layer that we found before. So a tephra layer is a layer of volcanic ash that gets distributed after a volcanic eruption. And we identified as the beta ash, which is an Icelandic eruption that is very well dated. So this could serve as a very good dating marker in the HDAC model. Then I was looking for the isolation, and I found that based on several of these proxies, that the lake must have been isolated around this depth in the core, so the isolation point is established there. And that corresponds to an age of 14,000 years ago. Then another find was the aggression contact, which means that the lake must have been inundated by the sea later on again. And that was very strongly indicated by the bromines you see here, and also by a change in hydrocarbon content. So the lake must have been inundated by the sea again around 11,870 feet. That was very brief, so if you have questions about it, I'm going to answer them. Then these reconstructions from both using Södergösevattnet, but also using the marine limit that I constrained through the speed book, these could be added to the pre-existing curve. So here you can see in black the sea level index points that were reconstructed before I started this project, and then the red ones are the ones that I reconstructed. What is, of course, of interest, especially in this study, is this period in time, the meltwater pulse 1A. And here, what we can see is that there's a quite gradual lowering of sea level until 14,000 years ago, when it starts to very steeply decline. And this is a little bit, later than what I expected, but it is what we have. And then another thing that's prominent in this curve is the younger dry ice stretch, which happened very regionally in southwestern Norway. It's not reflected in other isolation basins in Norway, just in southwestern Norway. Then moving on to the numerical modeling results. So first of all, I was very curious about the spatial pattern of simulated relative sea level change using this base run, so checking what I got out from that. And here it's very nice to show this difference between near field and far field, because wherever you see ice thickness reducing, you see a lowering sea level in close proximity to the ice sheets and rising sea level in the far field. So this shows the spatial distribution of relative sea level change as a response of changes in ice mass. And what is nice to note here is that the interval where meltwater pulse 1A takes place has especially strong relative sea level rise, partly in the near field, compared to the interval before and after. Then I computed the contribution of the Eurasian ice sheet to meltwater pulse 1A, the global sea level rise, and I did this based on all of the different runs that I ran, which was up to 36 runs. So I get quite a large range of what it could be, 1.27 to 7.25 meters. Yes, and then I wanted to know, okay, but which runs give a higher contribution and which ones give a lower contribution? So I take a look at all of the different runs and I try to show it in this plot. So what you can see here is that with accelerated ice thickness changes, so this is basically when I change the ice thickness more and more during meltwater pulse 1A, I get a higher contribution from the Eurasian ice sheets to meltwater pulse 1A. And then this chronological shift is very interesting because it's very different. it also, in general, gives a much higher contribution from the Eurasian ice sheet, so not what it calls one A, than the original thesis. So then the sensitivity of the sea level model. So whereas I discussed a global scale in this slide, I'm now zooming in on Buchan, and I want to know how sensitive the sea level model is on such a regional place in near proximity to the ice sheet, so in the near field. Because globally, I also tested that, it did not have as much to say when I changed different parameters, but locally it does, and that's what I want to show you with this graph. So here you can see the local relative sea level change in Buchan, and these results are compared to the base run. So to simplify, the base run uses the PM5A model. And for example, if I say, okay, I want to use a different Earth model, I want to use pattern 4, then I get up to 50% difference relative sea level change at my local site. So that's very little. And this kind of goes for all of the different parameters. The time series changes it substantially. The ice thickness adjustments also with increasing ice thickness adjustment. So what I can learn from this is that it's really important to have a large range of simulations because they can differ so much from each other, because it seems that the parameters are impacting each other most. Yes. For the synthesis. So first of all, I have plotted the relative sea level reconstruction for the isolation basins. And then I cannot show you all the runs, but it shows the pattern Earth model now. And then when I show you the run with no ice thickness adjustments and no time series adjustments, it looks like this. So it's quite different, and especially when we zoom in the time period of interest, which is not what it calls running. So you can see a gradual lowering in empirical data, but there is a gradual increase in the model run. So then I was curious, okay, but what happens if I change the ice thickness of the Eurasian ice sheet at different rates in this time period? If I enlarge a potential contribution of the Eurasian ice sheet in this time interval, does it then change the relative sea level change of Buchan? And it does. So here you can see the results from some of the runs. And on the different time series, it looks as follows. What you can see here is that the different time series has shorter time intervals due to the recalibration of dates between or in the period of interest. And that results in a much steeper curve here, a steeper lowering in sea level because the ice mass changes are happening on a much shorter time interval. Yes. So I looked at all the runs, and then I selected the runs that match the empirical data best in order to refine my computed contribution of the Eurasian ice sheets to number plus 1A. So then I see that the pattern 3 Earth model fits best to the empirical data, and the ice thickness reduction is 0.7 fits the empirical curve best as well. That's the purple curve. Yes, I want to stress here that this is highly dependent on the input of the sea level model though. So a different Earth model could avoid potentially this ice thickness reduction that I had to make. So that because they both impact each other, it's important to take it. But using this, I could give a most likely estimate of the contribution of Eurasian ice sheet to what it calls 1A, which was 4.7 to 5.58 meters. And then, of course, I want to compare to other studies, because that's what makes it interesting. And then I see that my large range is not improbable at all. It's within range of many of the studies. But my refined estimate corresponds extremely well, or especially well, with two recent studies, Lin et al. And Lin et al. 2021 and 2020, who have proposed an increased contribution of Eurasian ice sheet about what it was with. So to conclude, 3 new sea level index points for reconstructed for Buchan. the marine limit was further constrained to 21.73 meters above present-day sea level, and happened most likely shortly after the deglaciation of Hoeken. The sensitivity analysis of the model showed that relative sea level in the near field is highly dependent on the rheology of the Earth and the ice thickness history, and these impact each other. Model experiments estimate, so this is considering all model experiments, estimate a large range of contributions, but we can refine that using the empirical data. So this is really where they come in the combination, and that makes it a very nice approach. And then the findings in the study support this increased pre-burning marine reservoir age. This might be an improved age for Scandinavia. And then I really want to stress that high accuracy ice thickness histories and solid earth rheologies are crucial for simulating relative sea level in the near field area. So this was an example of how you can combine empirical data with modeling data and get a refined estimate of an ice sheet contribution to a global sea level rise. But for further research, it would be really interesting to use a wider set of empirical data to compare to, and then it should also be integrated with larger ensembles of simulations to better constrain the population duration action method of post 1A. Thank you, that was my.
Thank you very much. We have time for a quick question, if there is any.
Yeah, thanks for your presentation. It's really interesting to see what the focus project. With the models, the percentage that is I'm just curious because I don't know anything about modeling. Do you then just try to have a lot of different models to kind of eliminate this huge difference, or do you go by which model kind of fits the local needs?
It's a very good question. So this basically showed me how important it is to have a large range of simulations, and that is why, how to say, so I used different Earth models actually because of this, because I wanted to not base everything on one run. I wanted to see how different runs would give different outputs, and then from that I choose the best match with the empirical data. But of course it would improve the reliability of the study. It would have more runs, more Earth models, and for the Earth model especially, if it would fit better to the region. So I already tried to do that with the Platinum models. They were a better fit to southwestern Norway. Because, okay, maybe I should say first. Earth model, the lithosphere thickness. Sorry. It's a lot different. This varies around the entire globe, so it will not be the same at this point of the Earth. This one will be. So you want to choose an Earth model that matches the place where your study is best. And that is why I use different Earth models. And then for further research, I would really recommend to use even more parameters there to constrain it better, to be able to match the empirical data set. Yeah. Sorry, that's a long answer.
Thank you. I think we have to move on to the simulation. Thank you very much. Thank you to the audience. You will sit in the corner room?
Yeah.
Yeah.